Hey guys, I'm the one making this PowerPoint in this video today. So let's get started. Now this lesson is on the electron configuration, the quantum mechanical model of the atom. So if you remember last lesson on 2.2.1, we talked about the Bohr model, and we talked about the Bohr model and how Neil Bohr actually updated and built on the model that Rutherford has done before, and then it came to the really the it was actually a way to help explain what they were noticing when they're looking at the emission spectra. So, just a little quick reminder if you remember about the emission spectra and things. Why does it ask for subscription now again? So if you remember this, you're talking about, oh yeah, you have a gas tube filled with a certain type of element gas, and you pass energy through it. So it does give off. So it gives off a screen, and then you can see the different line spectrum. So one of the good thing about the Bohr model is that we have these readings of different wavelength. That is the emission spectrum. So how does it help us to understand how the atom looks like? And so in this case, it is actually good. The merits of it is that we actually help us to based on that. There's something called quantization. You talk about there's discrete, so specific energy levels. Okay, discrete energy levels. You can talk about electrons. Once they receive energy, they go from a lower state to a higher state, and then later on move back from the excited state down to the lower state. You sent out the energy. You also talk about the emission spectra of hydrogen, just like what I said earlier. Now, the math of it was able to be proven, but the problem is this. There's some problem about the Bohr model. Is that actually what we found out later on is that electrons not fixed model. These energy levels are not perfectly spherical, and not perfectly circular. Scale and size is not as the diagrams predict. Calculations good for hydrogen, but it's not for others. Okay, so we actually need to have a better model. And one of the things I really want to point out of this from this lesson is this. Now, this is from the chemistry guide. So, in some ways, all theory in when we're studying how atoms work, how the elements work, all theories keep on getting superseded, getting replaced when there's more data, more information. So, what we're learning today, quantum mechanic model, is the most current model that we're using. Okay. Um, and also another thing too, as you have better equipment, you have improved apparatus, you will also have more. You also have more data to come up with new theories. Okay, and the idea that we build these models is to explain what we can observe, to explain natural phenomena. Okay, so let's get let's get started. So really, what happened since Neil Bohr published his Bohr model? Now we have a number of these names. Don't ask me how to pronounce some of them. This one, even though it's by Neil Bohr, it has this name. It came from a German name, at least Pauli exclusion principle. You'll see this later on. Uh, Schrodinger equation. Again, that's another name that's difficult. Heisenberg's uncertainty principle. Um, there are a lot of discovery and inventions since Neil Bohr Uh, came up with his Bohr model. So in this case, what we're learning now, in terms of the quantum mechanics model, it is based on what people have done since 1913. Okay, so now a couple of things to really fully understand these things. It takes about second or third year university courses to understand. So to understand quantum mechanics, it's not easy. Now, I believe this slide deck will be shared with you. I have also went to Encyclopedia Britannica. So for each one of them, it is hyperlinked to the Encyclopedia Britannica. So if you really want to find out what those things are, go right ahead. The language is actually more understandable than Wikipedia, so go for it. But as I come back, to explain and understand all these things, it does take a lot of math, and it does take second or third year university courses understanding to get this. So if you don't get it, bear with us. One of the more important things, and as you notice, there are a lot of questions based on, is the electron configuration that comes later on. So let's get this going. So this guy, what he came up with a waves equation. So his waves equation back in 1926 helped to describe waves. And in some ways, along with Heisenberg uncertainty principle. Now, Heisenberg uncertainty principle state that it is actually impossible to find out where the exact location of every electron. It's impossible. Okay, just like right now, as you are watching this video, it's impossible for me to know exactly where you are. Okay, you might be in your room, you might be in your own living room. We don't know. Okay, hopefully you're in your house, but we don't know. The best we can do is come up with best guesses. Okay, so in some ways, this guy, I can't pronounce his name, he actually used math to predict the highest probability of where electrons would be at a particular location at a particular time. And it is really just a prediction. Okay, so in sense, rather than having orbits, okay, you come up with this idea of orbitals. Okay, orbitals, as it says here, is a region where we have a very high probability of finding the electrons where it has a particular amount of energy. Usually you're talking about 90 to 95% probability. Okay, so when you're thinking about orbits versus orbitals and pathway versus probability, in some ways, when you're thinking about orbits and pathway, it's more like you know exactly where things are. You know that electrons will follow this perfectly circular orbits. Okay, that's almost like old way of thinking. Okay, they always will be along this here, but actually, orbitals, after we use quantum mechanics, is it's really just what's the percent chance. So using baseball analogy, there's 70% chance the ball will be somewhere in this circle. There's 20% chance it'll get there. Okay, so when we're talking about probability, we're talking about like high chances. Just like I said earlier, I have no idea where I cannot be exactly sure where you are the moment you're watching this video. There's a high chance you're in your house, but hopefully you're not outside of the house, but I don't know. Okay, it's probability. Now, so in this case, in his wave equation, there are three numbers. Okay, think of it as almost like your address, so to speak. Where would the electron be at that time, at a particular time? So you have three quantum numbers. Okay, talking about the level of energy they have. If you want to think of it this way, quantizing the energy, it has a certain quantity of energy that is there. So you kind of know how much energy it has. So first number is the principal quantum number. You're talking about the main energy level of the orbit. So just like what you saw last lesson on the Bohr model, you have and level 1, level 2, level 3, level 4. So that's a principal quantum number. So it is built on the Bohr model, but we are tweaking a lot of it. Now, number 2, the second thing is that you actually have subshells. So each level, so level N1 has a different subshells. And so you call these subshells, you have a letter to it, S, P, D, and F. Okay, each kind of sub level has orbitals with a particular shape, so they all have some sort of shape. The shape does look very different. You're talking about where these things are going to be. Okay, chances of you finding electron in that area. So it's 90% chance, and all these are defined come up by math. So basically, a diagram would look like this: 1, 2, 3, 4. You have 4. So level 1, you have 1 subshell. Level 2, or shell number 2, you have 2 subshells. 3 will have this. 4 will have this. Okay, each subshell has a letter. Now, the shape of the shell. How does 1s subshell different from 2s subshell? So this is the part I'll ask you to pause, and on your Edpuzzle thing, write down your answer. How does it look different? Now, probably it's just look bigger. It takes up a lot more space. That's probably one of the big differences. But otherwise, shape-wise, it is somewhat the same. It just expand more. It's further away. It has a larger area of possibility, so to speak. Okay. Now, so s orbital was shaped like a sphere like that. P orbital will look different. Okay, P orbital, you have 3 possibilities. Okay, so if you look, you have they are dumbbell shaped like. So when you say px, so px look like this, py look like this, pz look like this. So in this case, going back to this diagram, if you have if something that has 2 shell have N2, shell number 2, you will actually have you can have 2s and 2p. So basically, if you look at your periodic table, which is you can briefly see through this, or I'll load this up again. If you look at this, all these electrons here at the second period, okay, would have actually, except all the elements from here onward, will have will have a 2p subshell. Okay, 2p subshell. I'm going to get into detail a little bit more later on when we're doing the electron configuration. But keep in mind, essentially, you have electrons either in this area, and this area, and this area. Notice that they are along the x, y, and z axes. And now, so when you're talking about the d orbital, now you're actually talking about planes. Okay, I don't know whether you guys learned this in math or not. So you actually have different planes. So this plane here, one plane, another plane, also another flat, another plane. I think this is inverted, and you have this funny shape thing over here. Okay, so you have these 3 orbitals. Yes, I know you have F suborbitals. You can look that up, but I don't think we need to know this, at least not according to the syllabus. So the subshells of a principal shell have a slightly different energy. The subshells of a shell of hydrogen have the same energy, but for multi-electrons, the subshells have different energy. Okay, that is one of the reasons why it didn't work for Bohr model. It didn't work for anything beyond hydrogen, simply because it was not able to talk about the electron-electron interaction. So I briefly talk about it just now. Any question? Just pause right now. Do you have any questions? Okay. Now, you have same idea. You have ground state of the electron is the lowest energy, higher electron orbital or excited state. This is same thing as the Bohr model. Now, so when you compare the Bohr model and the quantum mechanical model, both model can talk about the spectrum of hydrogen very well, but only the quantum mechanical level can talk about the other atoms, the spectra of the other atoms. Okay. So I'm going to pause here. Because we're going to be moving into electron configuration. So do you have any questions so far? Hopefully, when we talk about, if you have any question, write them down. Hopefully, after you watch the second video about electron configuration and how do we deal with it, hopefully they will make more sense. As I said before, we are just right now, all these things we're talking about, what happened. Yeah, all these things, I was just talking about is what happened from Bohr, published his Bohr model back in 1913, all the way till our current model of quantum mechanic model. What has happened? Okay, so in this case, we're just building up the case to this, so that we can start talking about electron configuration. So pause this, and if you have any, and we'll go after you kind of write down your question, move on to your second video. Okay.